I'll be giving an overview of the ECSS program, and then I'm going to go into a bit of a deep dive of a particular ECSS project that I had worked with Mao Yi on about 5 years ago. So when I do that, don't really focus so much on the particulars of the project. I want this to be more, just think of it as a case study of how these ECSS collaborations work. And then I'll talk about opportunities for collaboration beyond ECSS, how these kind of collaborations can often grow into something larger. So a little bit of background. I am not an economist or an expert in finance. If I say anything really dumb during this talk about finance, don't hold that against me. My involvement in this project is bringing the computational expertise. So when I worked with Mao, I was focused purely on the improvements to the computing. And this is very common in these ECSS collaborations. So John mentioned he's an astrophysicist. I'm a physicist. We have engineers, computational chemists. We have folks who come from many different backgrounds. But what they bring is that they have the computational expertise. Often something that developed, say, when they were in graduate school. They were getting involved with their research. They realized that they really enjoyed the computing, especially the high-performance computing aspects of it. And just another word about myself is, even though I work directly on these ECSS projects, now I have a broader role. I co-lead the ECSS program together with Phil Blood at the Pittsburgh Supercomputing Center. And I should emphasize that within XSEDE, we don't want to get into the management structure. There are 6 main components to XSEDE. One of them is ECSS, but it is such a large part of XSEDE that is the only component that actually has 2 of what we call the L2 managers at the, in the senior management level. It's a very large component of XSEDE. I believe that we have somewhere between 65 to 70 people who work in XSEDE, including the managers. Most of those are fractional FTEs or full-time employees, but we have a large base that we can draw on to do this. I would say the main theme of ECSS is that XSEDE is much more than high-performance computing. When people look at XSEDE, they tend to think of the hardware and the machines, and that's a very, very important component. But what XSEDE really brings is the expertise. In fact, XSEDE does not fund the hardware. These supercomputers that we've been talking about, Comet and Bridges and so on, are funded through individual grants from the National Science Foundation. What XSEDE does is it integrates all of these, provides some base services like allocations, and then also a lot of this expertise that you get through the ECSS. So within ECSS, so I should say ECSS, it's collaborations between researchers and XSEDE. We have expertise in a wide variety of areas. We do a lot of what I consider to be the traditional ECSS projects, performance analysis and optimization. We take a code or we look at it, figure out how we can make it run faster. We do software parallelization and scalability improvements. So if you have a serial code and you need to go parallel, we can help you with that. Also, if you have, oftentimes you'll have a parallel code, but you have limited scalability. And by that I mean you can only go out to so many cores or processors before your performance tails off. Ideally, when you take a code and you run it on 2 processors, you would like it to run in half the time on 4 processors in a quarter of the time, and so on and so on. Eventually, you reach a limit in the scalability, but often we can help you push that out further. We do gateway and portal development. Anirban mentioned very quickly what we call the science gateways, which are, you could think of as web interfaces to the supercomputers. These are great when you have a community of users who are using a common set of software. We can help you with specialized scientific software, visualization, putting together complicated workflows. And know a lot of what you do nowadays involves not running a single program, but running multiple programs and making them all work together. You can ask for advanced support or ECSS at any time. Often, when you make your allocation requests, you will ask for ECSS at that point. But even after you have an active allocation, you realize, say later on, that you need some extra help, you can ask for what we call a supplement for ECSS support. And that's actually very common. I should also add that ECSS is not intended just for the biggest, largest users. You might be thinking, well, I'm only using a few tens of thousands of core hours per year. I'm at the startup level. Isn't ECSS for the folks who have really, really large allocations, who are using millions of core hours per year? And the answer is no, it's for everyone. So we have some of our large users who are using ECSS, but ECSS really targets our new users who we want to make more efficient, who we may grow into being larger users. Requires written requests, but I'll show you in a few slides that it's not that hard. Okay, so under the hood, there are 5 components of ECSS. You're not going to have to worry about this. When you make a request for ECSS, you don't need to decide, is this something that fits under support for research teams or community codes or so on. I'm just putting this up here, though, to show you the breadth of what ECSS does. So the first two areas, what we call extended support for research teams and community codes, they do very similar kind of work. This is what I think of, again, as the traditional ECSS projects, where we help you to improve your software, to optimize it, to parallelize it. The difference between research teams and community codes is really more of the nature of the software, whether it's something that's used, say, within a lab or by a broader community. I would say with the community codes, we may have a little more emphasis on helping you with the software engineering. Because I was thinking, this is just my definition, but I think of the difference between code and software is code is something that you wrote to accomplish a task. Software is something that you can give away or distribute, that you could give to a colleague who could then use it without you sitting there right next to him or her, helping them to use the software. We have this extended support for science gateways that can help you build one of these web interfaces to the supercomputers. So it abstracts away a lot of those low-level details. How many cores do I want to run on? Do I want to use GPUs? Which system? And so on. We could build a lot of that logic into the gateway so that the end user can focus purely on the application. We have something else called NIP, Novel or Innovative Projects. And this is really focused on getting users from domains that are relatively new to XSEDE and high-performance computing, getting them started. And then finally, we have extended support for training, education, and outreach. This gives us the technical support for using the advanced cyber infrastructure. So we already talked a little bit about training, and ECSS does have a component of that. So how do you get ECSS? Pretty easy. Just need to make requests, answer 5 questions. First of all, we want to know what you want to accomplish with the help of the expert staff and whether or not you've done any work on this or done any work on this already. So let's say you have an application, it's serial or it's too slow, it's just taking too much time, and you want to make it run faster, you want to be able to run on a parallel machine. That would be a good justification. And we'd like to know what steps you've taken already toward doing that. We want to know how the success of the collaboration would benefit your project. We want to make sure that it's going to have an impact on your science and your research. So for example, if you have an application software that you need to run once a year and it takes 5 hours to run, it might be fun and interesting to work on that code to make it run faster. But if we could take that code that runs once a year for 5 hours and cut the runtime in, reduce it by a factor of 10, that doesn't really impact your research. It doesn't have it won't make you more productive. We want to know, is this the application, the workflow, something that you're using on a daily basis, something that, boy, if I could go from, it takes me a week to do something to I could do it overnight, or I could do it within an afternoon. That makes a big difference. Would it make you more productive? We also want to know what members of your team are going to be collaborating with our staff. And this is really important. We talk sometimes about taking the code and throwing it over the fence. It's like, hey, here's my code, work on it, let me know when you're done, give it back to me. That is not the way we work. Remember that the C in ECSS is collaborative. There needs to be somebody in your group who's working with us. It doesn't necessarily need to be you, the PI of the allocation. I know as we get further along in our careers, we do a lot less C and Fortran and Python and R programming, a lot more of, as John said, proposals and grants and presentations. But somebody within your group, we need to have somebody who we're going to be working with. We'd like to know, did you work with anybody within XSEDE before? Oftentimes, you may have been working directly with somebody at one of the supercomputer centers who is also an ECSS consultant. You may have you may know them personally. They may have helped you with an application. You may have been put in contact with them through user services. If you already have a relationship with somebody who does ECSS, and it's already working, you may want to follow up and specifically request that consultant. We can't guarantee that we could always do that match, but if possible, we do. And then finally, we want to know if you've had ECSS support in the past. There's a lot of demand for ECSS, so we want to make sure that that we make this broadly available to the community. And if you did have ECSS in the past, we want to make sure if you're requesting it again, that it's for something new or for some new aspect of your project. And we do have many what we call repeat customers. It's loud, but we just want to know what the history was. I know you're not going to be, you won't be able to read this, but this will be distributed in the slide decks. Just gives you a listing of the current ECSS projects, including, and this is just one small snippet, and there's also a very large table with past projects that have been completed over the years. If you look through the list of project names and they don't make sense, don't worry. These are from just about every field of science, technology, and engineering. But there are a few in economics and finance in there. So with that, I'm going to dive into a case study. About 5-6 years ago, I had worked directly on a project with Maui. It was a lot of fun. I learned much from it. My limited knowledge of economics comes from reading a few of the popular books like Freakonomics and from talking to Mao. So it was a great experience. Big success. We were able to take the time that it required him to construct limit order books by a factor of about 100. So I'm hoping that was a bit of a game changer for his research. Now, actually constructing a limit order book, I think within the economics and finance community, is really a pretty dull activity. You're taking data, you're manipulating it, but you're generating data that's absolutely essential as a jumping off point for much deeper analysis. So I didn't get into that. I just focused on the construction limit order book, which makes it much easier for Mao then to get all of this data and jump off and do the really interesting stuff. And then finally, as they like to say, past performance is no guarantee of future results. We don't always get 100x speedups. Or in this case, if you include the follow-up based on NSF-funded work that we had, compounded by another 50x speedup, that's kind of exceptional. But sometimes we do, have a real home run. Okay, so I won't go too much into the limit order book. Mao talked about this a little bit already, and I think we're just a little over time. But market data consists of 17 different types of messages describing various activities, orders to buy and sell, execute orders, delete orders, update orders. So there's really just a handful of these that we're directly interested in. Limit order book is really just a record of those unexecuted orders. But then once we have this limit order book, we can calculate all sorts of things that folks in computational finance are interested in. So again, this work was to help Mao get to the point where he could generate these limit order books very, very quickly on larger data sets and that dive in and start doing the more interesting work. So you saw this slide already in Mao's presentation. One thing I want to point out, though, is that this limit order book, the raw data that we get, it's in something called the itch format. It's a binary format, extremely compact. In fact, it does things like to reduce space. It won't contain redundant information. So if there's a order to buy, of course, you need to provide the stock symbol. But if there's later an order to cancel or update, the stock symbol is not included so that we could save space, because these are large data files. So there's a complex bit of manipulation that has to go on. And here's just an example of a sample limit order book. Oh, but going back here, another complexity with the limit order book construction is that when we go to the itch data, it is a sequential list of all of the messages that were posted. And it's not broken down by stock or symbol. These are all interleaved, so there may be and they're all ordered by time. So it might be a order to buy Amazon, and then to buy Google, and then to buy something else, and then to cancel the Amazon order, and then to buy another stock. So there's a bit of work that has to go into processing this data. So I had a slide in here. I took out the comments. Just say that there are some implications for high-frequency trading. Okay, so the data processing pipeline. When I started working with Mao, there were 3 steps. The first was where we had to take that itch data and convert it to a text format that we could work with. If you've ever worked with the itch data, it's kind of ugly. Not only is it binary, but they use weird data types. There's things in there like 6-byte integers, these various custom data types, so that they could really compact the data. They figure if they could get away with a 6-byte integer instead of using an 8-byte integer, which is more standard, they could save a little bit of space. So we need to convert that to text format. We then need to process that and add in extra information. And then finally, what I have here is the big red arrow, is the lob construction. And that's a step that was taking a lot of time. So to give you an idea how expensive these could be, we looked at some data. These were from the day of the famous day of that flash crash on June 4th, 2010. This was using the original version of the code, using all 16 compute cores on a node of the Gordon supercomputer. This is one that now our older supercomputer. And these were a few of the stocks that we're looking at, and the time that it took to construct the limit order book. And this is in seconds. So if you're trying to do the math in your head, the 8,400 seconds is about 2.5 hours. For Apple, a lot of activity that day. That 129,000 seconds, I think, comes out to about 44 hours. So a lot of time to construct the limit order book just for a few of these symbols. The other takeaway here, and I'll get back to this later, is you can see that there's quite a dynamic range there. Going from 8,400 to 129. But the dynamic range is actually much, much larger than that. It's about a factor of 1,000. So some of these symbols, we can construct the limit order book in the blink of an eye. Other ones could take more than a day and a half. So we consider this to be a rate limiting step. So we wanted to figure out, okay, can we make this software run faster? And again, just think of this as a particular case study of the kind of things that we can do in ECSS. So I'm going to go through these next few slides pretty quickly. I realized I was putting this together on a Saturday morning. Most people don't want to stare at PowerPoint slides filled with C++ code. But that said, we're going to do a little bit of that anyway. Well, don't worry. If you're not a C or C++ programmer, don't worry. We're not going to get into the details. But across these 4 slides, I originally put these together for a different group, basically my peers who do these ECSS projects. So first of all, we profiled the code. We figured out where is the code spending most of its time. We're able to narrow it down. And for each of these optimizations, we have kind of a particular theme. In this one, I call it do things once. So we're reading in the data, trying to construct the limit order books. And we noticed that within some of the loops, we were spending a lot of time over and over every time we had a character string that we're converting it to an integer and then doing some operations on it. And internally, that's a fairly expensive operation. So we created a few additional data structures. We would do that once. We'd take all of this character data, we would convert it into integers, we'd save that in another data structure, and then we would reuse that over and over. Next thing we did, we started with a parallel version of the code. It was parallelized using a very low-level approach called p-threads, parallel threads. And we realized that there was a critical region within that code where all the threads would be doing their work, and then they all need to write to a file. And each time one of them writes to the file, it has to say, hey, everybody stop what you're doing, wait till I'm done writing to this file, now I'll release the lock and somebody else can write to it. So you have all this serialization. So what we found is that when we ran on 16 cores, we didn't run 16 times faster, we ran about 5 times faster. And it was due to this serialization. So we did a little bit of restructuring so that we could have each of the threads write into their own temporary data structures, dump everything at the end, and then we got near perfect scaling. Another thing that we did was what we call dynamic scheduling. So they're at a very high level, there are, I think, what I think of as two main approaches to parallelization. That there's a static decomposition of the work and a dynamic decomposition of the work. So static would be, let's say we have 1,000 tasks that we need to do, and we get 10 volunteers, and I hand them out. The first 100, the next 100, the next 100, the next 100. So each of you are getting, each of the 10 volunteers are getting 100 of these tasks. Now, if you're all equally capable of doing these tasks at the same speed, which of course computer cores are, and each of those tasks take the same amount of time, we're going to get good load balancing. What happens, though, is that often the amount of time required for each of those tasks can vary by quite a bit. So if there's an imbalance, we're going to find that we're going to have some of the cores are going to finish early, other ones are still going to be doing their work. So we took some of these key parallel loops, and we instead did a dynamic decomposition, where in this case, say for our 16 threads or our 10 volunteers, we take much smaller units of work. We hand out some to everybody, and then the first one that's done essentially says, I'm done. They get another chunk of work. Somebody else raises their hand, I'm done. They get the next chunk of work. So by doing this dynamic decomposition, we could get a lot better performance. And then finally, the last optimization we did was, again, kind of at the scalar level of the code, is we looked at some of the loops. They had conditions that once we know that condition is met, we don't need to do any more iterations. So we put what we call break statements in there to break out of the loop early. In fact, I should have reordered these slides because we did this first and realized that it introduced a new load imbalancing. Then we went back and we implemented the dynamic decomposition. So it's just kind of a smattering of the kind of techniques that we could use to make the code run faster. Within the group of ECSS consultants, these are things that are very well known. Okay, so what was the impact? Looking at those 3 very expensive symbols, for our first column, I have that original time, the 8,400 seconds, the 129,000 seconds, and the next column I have the time for the modified code. And we see that we got speed ups ranging from about 66 to 113x. So I'll just say we got about 100x speed up. So already Mao is going to be much more efficient. He's going to be spending less time worrying about this, what I think of as from a finance point of view, not a very interesting task. It's just something that you need to do so that you could get on with your research. So then, in the beginning, he was originally working with just a subset of the data. He would take, since it was so computationally expensive, he would take maybe 120 symbols and work with those. And I said, hey, we've got this running a lot faster. Why don't we see if we can do entire markets, which I think is what you really want to do. So we looked at 3 different days. We picked days that we considered to be very challenging, where there was a lot of activity. There was the day of the flash crash, the day of the night capital computer glitch, and then actually from just a typical day. And I won't go into all the details here. It's showing some runtimes across different machines. But essentially, we got to the point where to construct these limit order books, depending on the day, we could do it for an entire market for all for all just under 3,000 symbols in anywhere from 2 hours for a typical day to about 10 hours for a really challenging day. And remember that top table there for the day of the flash crash, 10 hours. That's 10 hours for the entire market. Whereas just one of those challenging symbols, I believe it was Apple, was taking us about a day and a half. So we've really made it much more productive. Okay, so next part of the talk is about going beyond ECSS. So ECSS projects are of limited duration. They're initially for 1 year. They can be ended early if the goals are met. Sometimes this happens. I've had a few projects where I worked on. We looked at our work plan. It's like, hey, we're done. So we could wrap that up early. But if there is more work to do, they can often be renewed. And they're also limited by the level of effort of the ECSS consultant. So this is a very valuable service. You're getting essentially a quarter of a person's time. And we have a large user base that we're trying to serve. There's a limited level of effort. Sometimes we can have multiple consultants working on a project, but often they will work at a little bit lower level. Okay, so I got 5 minutes. Okay, can I go about 5 minutes over just since we started a little late? Okay, thank you. All right, so I'm saying here that ECSS can often seed the initial work that can lead to an externally funded collaboration. And in this case, I think we needed to do that. So again, our first project was, it was very successful. We got that 100x speed up, but we realized there was more to be done. If any of you have worked directly with Mao, and I mean this in a very good way, you'll notice the pattern that there's a certain goal. They say, okay, now that we could do this, let's do something else that's even more ambitious. So there's always going to be something bigger that you want to do, which is good, which is exactly how we want you to think. John mentioned earlier, don't think about the how, think about the what. Think about what is the problem that you would really, really like to do if computing was not a bottleneck. So we want to get a little more ambitious. We realize, though, that this required a complete rethinking of some of the algorithms rather than just tuning the existing algorithms. We had to do a little more advanced work to make optimal use of flash storage. So we applied together for an NSF Eager Award. So Mao was the PI and as the co-PI on that. Of course, Mao's work focused on the finance. I was focusing on the continued focus on the fast construction, these limit order books. So we realized, we wanted to do combined analysis of all stocks across multiple markets on very busy days of activity. So we wanted to further reduce the time to solution. We also needed new algorithms to reduce the memory footprints. As Anirban mentioned earlier, we have these large memory nodes, but they're kind of specialized hardware. Sometimes they're in very high demand, and if possible, you don't want to be tied to a particular hardware. And we also need to think of data management strategies for working with large input data and file counts. So I could go through this pretty quickly. Gives you a summary of what we did. We started with that message data. We would first take it, we would split that into chunks. Just going through sequentially, breaking it into chunks. For clarity, I'm only showing 16 processes, but this could be extended to all of the cores on a shared memory machine. And then for each of those chunks, we split those into stock or symbol specific chunks. So remember I said how all that itch data is interleaved. So now we have, for example, from chunk 1, we have the data specific just to Apple and just to Google and just to NVIDIA. And then for chunk 2, we do the same thing. Here I'm only showing the 3 stocks, but we could extend this to an arbitrary number. Then we combine them together. So in these first 2 steps, we've essentially taken that itch file with all the interleaved data. We've split it, we've recombined it, and now we have one separate file for each symbol. We then construct the limit order books, and here I'm doing a different kind of parallelization. Here I'm doing parallelization instead of within the code processing data for stock. I'm doing the parallelization at the level of the stocks. Now remember I mentioned earlier that there's a great dynamic range, at least at least 3 or 4 orders of magnitude in how long it can take to construct these limit order books. So we developed a dynamic scheduling approach where we're essentially handing out the work to the processors. Whoever got Apple might only work on one symbol. Somebody else might work on multiple symbols. So we're able to get very, very close to linear scaling. And then when we're sorry, I see a slide got lost here. But we take all these limit order books, we then combine them into a large archive that contains all the data, and you could post-process later. So what happens? So now we got another 50x speed up over what we had earlier. So now we're talking a few thousand x speed up. The other thing to notice is that we really reduced the memory footprint. For some of these cases, if you look at that second last column, original memory, was 29 to 59 gigabytes. That's not too much. But as we went to these more ambitious problems, we're going to be spilling beyond what's available on standard hardware. If you look at the last column, though, with our new algorithms, rethinking the data structures, we're able to reduce that down to just a few gigabytes. So as I mentioned, when you work with Mao, there's always a more challenging problem that he wants to tackle, which again is a very good thing. We want you all to be thinking about that, thinking about what is the thing that I would really, really want to do. So now we extended this to, I think I got this right, combined New York Stock Exchange, NASDAQ, and BATS on the heaviest days of trading to date. So this work was done a little while ago. If you look at these last 2 columns, total time to solution, you'll see there, and this is in minutes and seconds now, it's about 2 hours. If we had used the original version of the code, we estimate that it would have taken 2,400 to 7,200 hours just to construct the limit order book, which is a long time to wait before you can dive in and again start doing the interesting work. So hopefully this was able to make everything much more efficient. So with that, I guess we did finish right on time. So I hope from this that you got an appreciation for how we can benefit from XSEDE's ECSS program. Again, this was just one specific example. We have folks with expertise in a wide variety of areas in high performance and high throughput computing. And I'm hoping that we're going to get some more XSEDE users, and we're looking forward to working with you.